Math 1314, Tyler Junior College, Section 3.2, Polynomial Functions. End behavior, the leading coefficient test. I'll go ahead and come out and say it. If I invented math, I would not call the following conclusion the leading coefficient test. I would call it the leading term test. You'll see why in a moment. But first, let's talk about what we mean by end behavior. And remember, we're trying to transition from quadratic functions whose graphs are predictable, parabola opens up, parabola opens down, to a generic polynomial function which may not have as predictable a graph. But the truth is, it is predictable, you just got to know what to look for. When we had a quadratic function, the ends of the graph were predictable. If the parabola opened up, then both ends would rise, both ends would point up. But if the parabola opened downward, then both ends would fall. We would say that both ends point down. Well, we would say that the ends fall. Since the end behavior is doing precisely that, describing the behavior of the ends, there's only 4 possible combinations in terms of rising and falling. For example, for this first graph, f of x equals x to the 4th minus 9x squared, whose graph I've roughly sketched here, we could say that it rises left and rises right. Now I take a little issue with saying that this graph is rising on the left because it's actually decreasing coming in. So keep in mind that we're not reading the graph left to right like we normally do when we're describing the ends. We're just simply saying the directions that they're pointing. So even though this graph begins by decreasing, we say that it rises on the left. Now we can also say that both ends rise, because both ends are pointing up. Sometimes the ends are equal, sometimes they're opposite. For example, on g of x equals x to the 3rd power minus 2x to the 2nd power minus 9x plus 18, the ends are opposite, because on this one we would say that the left falls, or it falls left. I'm trying to be consistent with the particular textbook I'm using for reference. Don't know why, I'm doing this independent of a textbook, so to speak. We could say it falls left and rises right. So that's how we could describe the end behavior of that graph. How would you describe the end behavior of this next one? H of x equals negative x to the 4th plus 9x squared. Well, both ends are pointing down, so we could say that it falls left, and we could say that it falls right. But because both ends are doing the same thing, we could just say both ends fall. By the way, this function was just the negative of the other one. I just stuck a negative in front of this and distributed it. Do you remember what that does? Reflects across the x-axis. That's how I got this one too. How would you describe the end behavior of j of x equals negative x to the 3rd power plus 2x to the 2nd power plus 9x minus 18? Since the left is pointing up, we could say the left rises. Excuse me, trying to be consistent. We could say it rises left and falls right. So again, on this one, the ends are opposite. One rises, one falls. In fact, on 2 of them, the ends are opposite. The 2nd and the 4th. On 2 of them, the ends are equal. The 1st and the 3rd. But our objective isn't just to be able to describe the end behavior. Our objective is to predict the end behavior prior to drawing the graph as a means for helping to draw the graph. So now the question is, where in each of these functions would we look to predict the end behavior of the graph? Well, when we had a quadratic function, like f of x equals negative 5x squared plus 7x minus 4, where did we look to determine if the graph was an open up parabola or an open down parabola? The answer was here, the leading coefficient. Actually, there were 2 things that determined the shape of this graph, not just the leading coefficient, but the fact that the degree was 2. So the 2 told us the shape, and the degree kind of told us the direction it opened. So on these, we're also going to be focusing on the leading term, and more specifically, the leading coefficient, and the degree. So let's focus on those. For the first one, well, for all of them, just like in the case of a quadratic function, our only concern with the leading coefficient is whether it's positive or negative. In this case, the leading coefficient is positive. So we'll say LC is greater than 0. Same thing with this one. And for the other two, the leading coefficient is negative, less than 0. Leading coefficient here is -1, and here is -3. So can that help us sort out whether the ends are equal or opposite? Well, not really. Because if you notice on both of these, the leading coefficient is positive, but here the ends are equal, they both rise, and here the ends are opposite. The left falls and the right rises. So if the leading coefficient being positive or negative can't tell us if the ends are opposite or equal, what can it tell us? Well, look at these two graphs and specifically their ends. What do they have in common? On both of these graphs, the right end rises. Well, what about when the leading coefficient is negative? What do these two graphs have in common in terms of their ends? On both of these, the right falls. So, if the leading coefficient is positive, the right rises. And if the leading coefficient is negative, the right falls. So what we can say is the sign of the leading coefficient, LC, determines the right end behavior. Positive leading coefficient, right end is positive. Negative leading coefficient, right end is negative. Positive, negative on the right. Okay, so that's helpful, but it's not sufficient. Because our leading coefficients could both be positive and both ends on the right could rise, but the left ends are still opposite. Over here it rises, but over here it falls. So what can we use to discern between whether or not the ends are going to be equal and whether or not the ends are going to be opposite? Remember, we're focusing on the leading terms. And I kind of set this up to draw maybe a false conclusion, but maybe we can draw the one that I want us to draw. Let's look at the ones where the ends are equal, the first one and the third one. And remember, we're focusing on the leading terms. But we can't focus on the leading coefficients. We've already decided what that tells us. But we can focus on their degrees. What do the degrees of the first and third function have in common? Well, I know they're both 4, which is my fault for making them the same, but there's something else that they have in common. I'll give you a hint. If I change this 4 to a 6, we may get some more wiggles in the middle, but both ends will still fall. And if we change this 4 to a 6, we may get more wiggles in the middle, but both ends will rise. So I think you can probably see now that what makes both of these ends equal relative to the degree is that the degree is even. So this one has an even degree. The first one and the third one both have an even degree. Now we haven't checked the others, but if we're going to say that an even degree gives us equal ends, then what do you think the counterpart to that is? That an odd degree gives us opposite ends. Let's check it. The degree here is odd, the ends are opposite. The degree here is odd, and the ends are opposite. And you might go, well, maybe it's just because it's a 3. Well, no, it's not. I'm just telling you that if it were any other odd degree, we would still have those opposite ends. So here we have an odd degree, and we have an odd degree over here as well. So what can we say about the parity of the degree? The word parity, which I don't use too often in an algebra class, means whether a number is odd or even, whether a whole number is odd or even. So either the parity is even or the parity is odd. So what can we say about the parity of the degree? If the degree is even, then the ends are pointing the same direction. Or as I like to say, if the degree is even, the ends are equal. ends are equal, meaning that they both rise or they both fall, and vice versa. If the degree is odd, the ends are opposite. I know this isn't a composition class or a literature class, but that doesn't mean that I don't know what alliteration is. Maybe you know what alliteration is. It's when words begin with the same consonant sound, or vowel, but the same sound in general. In this case, it's all vowels. Even, equal. They both start with E. Odd, opposite. They both start with O. Now, this is not what a lot of teachers will teach. I like to teach it this way because it's a natural consequence of analyzing 4 graphs with the 4 different types of end behavior. What some teachers will teach you, what some books will teach you, is not the things in blue, but the things in red. Under these circumstances, we get this. Under these circumstances, we get this, etc., etc. But the way they summarize it is normally in a table, a 2x2 table, which I will write over here and keep for the next video. Because we're asking 2 binary questions. Binary meaning it has 2 answers. We're asking the question about the leading coefficient being greater than 0 or less than 0. And we're asking about whether it's an even degree or odd degree. Remember, if the sign of the leading coefficient tells you what the right end does. Positive leading coefficient means the right rises. Even degree means equal ends. So under this circumstance, we have both ends rise. However, if the leading coefficient is negative, that tells you the right end falls. Even degree means equal ends. So if the leading coefficient is negative and the degree is even, then both ends fall. But for the odd degrees, they're opposite ends. So positive leading coefficient means that it rises right. But if they're opposite ends, that means it falls left. But if the leading coefficient is negative, that means it falls right. But odd degree means opposite ends, so that means it rises left. So if you want to memorize this table and hope you put all the words in the correct place, be my guest. But if you can understand that leading coefficient tells you what the right end does, rise or fall. Even says equal ends, odd says opposite ends. Then you can reconstruct that table. But usually you just need one type of end behavior at a time, so I would just analyze the degree and the leading coefficient to answer whether or not the left rises or falls, as does the right. In the next video, we'll take a look at a couple of examples. Warning, I'm going to try to trick you on both of them.